Earlier we have discussed magnetic vector potential. The magnetic vector potential arises from the fact that divergence B is zero always, so which suggests that B can always be written as curl of A. This is always this result is valid. In general, the magnetic field is not conservative, as Ampere's circuital law in its differential form gives us this result, that is, curl of B is not zero at a point in space which is being occupied by a current density. If the point under consideration is not occupied by any current, if that is to say, if the current density is zero, that is in a current free region, we have J is the null vector, and hence we have divergence by curl B is equal to 0, which readily suggests that B can be derivable from some scalar point function. Conventionally it is written as this, and this is known as magnetic scalar potential. If we consider the permanent magnet, that is a magnet produced by the North Pole and combinations of North Pole and South Pole, then the calculation of scalar potential is exactly similar of calculating the electrostatic scalar potential due to a dipole. But here we want to do something else. We want to calculate magnetic scalar potential due to a distribution of current, and the field point is so chosen that there is no current, so we can define scalar potential at a current free region. Remember this that this magnetic scalar potential is valid only when the region under consideration is free from current. On the other hand, vector potential can be applied everywhere, whether the point under consideration is occupied by current or not. So our aim is to calculate phi m magnetic scalar potential due to a current loop. Phi m due to a current loop. As usual, we consider a current loop which carries a current I, and the current loop is a small one, so it is assumed to lie in the plane of the board, which is the Z is equal to 0 plane. It carries a current I in anti-clockwise sense. We consider a length current element I dr prime around r prime, and we are interested in finding out the scalar potential at P, which is R, and this contour is C prime. So this is our aim. We want to find out the scalar potential at P due to this current loop. We start with the fact that change in scalar potential phi m is given by that is, if we make a shift of the field of observation point from r to r plus dr, the field point changes from vector r to r plus dr, then there will be a change in the potential, because at point r the potential is phi m at r, and at this point the potential is phi m at r plus dr. If we consider dr to be small, we can approximate it as d phi m at r. Here we have performed Taylor expansion, that is, this part is actually equal to grad phi dot dr. So this is the change in potential due to change in the field position by an amount dr. So is equal to this is now we replace this by the defining equation of the scalar potential, that is 1 upon mu 0 times B dot dr. Note that B is defined to be B at R is defined by this. Now here B is the field at P due to this current loop. So according to Bauer-Savart law, we replace it by mu 0 I upon 4 pi integration dr prime cross R by R cube times dr. Here we have replaced the B at R due to this current carrying loop. The integration over C prime is mu 0 I upon 4 pi this is as per Bauer-Savart law. You see that this dr prime is this length element and R is the change in position vector, thus dr position vector of the field coordinate. We can in this picture what we have done is that we consider the ring, the current carrying conductor, to be stationary, and we change the observation point by an infinitesimal amount. So some changes will occur and the change in potential is given by this. Instead we could do one thing else. We could keep the field point fixed over here and shift the conductor in an opposite direction by an amount dp. That is to say, we shift the conductor by this amount. This dr here is clear. So this is the original position of the conductor. This is the shifted position of the conductor. This is the shifted position of the conductor. So the shift is by an amount dp. So the shift is an amount drp. So we shift it by an amount drp, so that drp is equal to minus dr. And this is a passive way of looking at the situation. That is, if we consider that that a body is rotating when viewed from a fixed coordinate system, instead the situation could as well be described by considering the body to be at rest and the coordinate system is rotating in the opposite direction. Exactly the same thing has been done. Instead of shifting the field point, keeping the conductor fixed, we have made the field point fixed and shifted the conductor in the opposite direction. In that case, this becomes, this mu 0 cancels out, I upon 4 pi, and this sign is plus, and this becomes dr prime cross R dot drp upon R cube where drp is equal to minus dr. Now you see this is the dot product as scalar triple product, so order can be interchanged. We suitably interchange the order like this: I upon 4 pi we have made two interchanges, so the sign remains the same. Now this is drp, in fact this is drp and this is dr. This is drp and this is dr prime. So the cross product gives the area, and the area of the rectangle of which drp and dr prime are the two adjacent sides, and the area is the direction of the area is governed by the cross product rule. In this case, it is directed it is in the plane of the board and directed away from us. So we can call it as ds prime. Let me call it where ds prime is equal to drp cross dr prime. So this is the area. In fact, this is the solid angle that this area makes at the observation point. It is this solid angle is governed by this, and the solid angle is d omega. So we call it, this part is d omega. Where d omega is equal to ds prime dot r upon r cube. It is the solid angle subtended by the current element. It is solid angle subtended by the current element I dr prime between its original position shown by the blue line and the shifted position shown by the black line at the point of observation. So this is the solid angle. And if we integrate over the contour, what we get is the total solid angle that is being subtended at the field point by the entire conductor between its original position and the shifted position. That is, if we have, this is one position of the conductor, and this is the shifted position of the conductor, then the area traced out by it is this, and the area element, if we consider the field point, this area subtend a solid angle that will be obtained by integrating it over the space. So this is I upon 4 pi d capital omega, where d of capital omega is equal to c prime d omega. This is d of capital omega is the solid angle subtended by at the field point by the entire conductor between its original position and the shifted position. The solid angle, so if we consider the solid angle, if if we look at the area element from the field point, if the area element be thrust in the opposite direction, in anti-clockwise direction, then the solid angle is considered to be positive, and if it is be thrust in clockwise direction, then the solid angle is negative. So what we come across is that the scalar potential, change in scalar potential as the field point changes by an amount dr, vector dr, is equal to I upon 4 pi times the solid angle subtended by the current loop between its original position and passive shifted position. The passive shift is exactly same as the change in field coordinate, but in opposite direction. Now, if we want to integrate it to get the scalar potential at this point, then we must integrate it between its present position and a reference position or standard position. In standard position, we assume the field, the conductor to be at infinitely large distance, which since the conductor is of finite extent, it extends zero solid angle at the field point, and when it is taken to its present position, it gives you the total solid angle subtended by the conductor at the field point. That is to say d phi m is integrated from 0 to phi m. In this case, I upon 4 pi is constant, and d omega is between 0 to omega. This is the standard position when the conductor was at far away, which subtends zero solid angle. So finally we get phi m is equal to I upon 4 pi sigma omega, where capital omega is the solid angle subtended by C prime, the contour, at the field point at P. This is as simple as this. Now, this is one way of calculating this. The thing to be remembered is that the angle, the unit of angle is radian, and and that of solid angle is steradian, and the scalar potential will have the dimension of current, and if we have a current carrying conductor which carries a current, if we want to find out the scalar potential at this point P1, then when we look down to the conductor from P1, the current is found to flowing in anti-clockwise sense. So the solid angle that will be subtended by the conductor over here is positive, omega is positive. If we consider the point a point P2, which is below this, from whenever we look at this, the current is flowing in clockwise direction and omega is negative. This is the convention used. Another thing which will be of interest is that what is the differential equation that you will be so satisfied by the scalar potential. Now, we know that the defining equation for the scalar potential is that B is equal to minus mu 0 grad of phi m, and we know that divergence B is 0. When we use these two, we find that 0 always. So it is always whenever it is provided, whenever it is defined. So magnetic scalar potential for is not always defined, it is all defined only in the case of region free from current. This equation leads to the boundary value problems of magnetostatics, which can be solved using geometry, as in the case of spherical surfaces, or other things which will be done in connection with the Legendre and Bessel functions. Here we shall go to another aspect. We shall calculate the magnetic scalar potential at an axial point due to a circular disk, current carrying disk. So what do we have? We have a, let me first draw this graph. We have a circle which carries a current I. We choose the circle to lie in the xy plane, such that the origin coincides with the center of the circle. Our aim is to find out the scalar potential at a point on the axis. If this point, this axial point is considered to be the z-axis, then we are to calculate magnetic scalar potential at P, and this is the current flowing in the anti-clockwise sense. Because the system has a cylindrical symmetry, we choose a cylindrical coordinate system and consider an area element this at around r prime. So the area element ds prime, it will have the magnitude rho prime, d rho prime, d phi prime, because it is an area on the z is equal to constant surface. So the direction is this, and rho prime will be, r prime will be rho prime cap rho prime, where rho prime ranges from 0 to a. The field coordinate r is k cap z, so that the r relative coordinate is r minus r prime is equal to k cap z minus rho prime cap rho prime. And so the solid angle that is subtended by this area at point P. So note that this capital omega is not the capital omega, is not the same sense that we used in the earlier development. In earlier development, d omega was used to denote that the solid angle subtended by the entire current loop at the field point between its original position and the shifted position. Here d omega is the solid angle subtended by this area element at the field point. So this is equal to now come to the dot product. It is along k direction, so only this part will contribute. So this is rho prime, d rho prime, d phi prime, z, the numerator part, and the denominator is denominator is this cube, so this is rho prime cube plus rho prime square z square to the power 3/2. If we want to find out the total solid angle that is subtended by at point P, this is the integration of solid angle over circle of radius A. That is, this phi integration gives you 2 pi and z is taken out, so this is 2 pi z is taken out, and the resulting quantity is rho prime d rho prime square z square to the power 3/2 integrated from 0 to A. Now if we use the substitution u is equal to rho prime square plus z square, then the integration becomes in the numerator we will have u du, and in the denominator it is u cube, so the result is du upon u square, that is minus 1 upon u. That is, the result is 2 pi z with this minus sign 1 upon u is equal to rho prime square plus z square within limits 0 to A. So the result is we adjust the if we use the lower limit first, then it is 1 by mod z minus it is a square plus z square to the power half. So the vector potential, the scalar potential phi m is equal to I upon 4 pi times sigma. So if we use this, it is I by 2 then z by mod z minus z upon a square plus z square square root. If the point of observation lies on the positive z axis, then this is plus, and if the point of observation lies down the z axis, this part is minus. So we write it, the result for z greater than 0, and for z less than 0 the result is let me write it first. This is equal to I by 2 1 minus z upon a square plus z square half pi z is greater than 0, and this is equal to I by 2. This part is minus 1 and this is plus 1. When z is less than 1. The factor, the solid angle, if we consider 2 points exactly, z away, one along the positive z axis, one on the negative z axis. For the positive z axis, the solid angle subtended is a positive quantity, and that's why this is the expression for the field, and for the point down the z axis, the solid angle is negative. That is the result over here. If we consider a small current loop, and if we consider a small current loop or elementary current loop, is this a current loop delta C prime, which bounces which substance solid area this, and we want to find out field at point P which is far away. Then the scalar potential, this delta is for the elementary loop, or let me phi m for an elementary loop. So if we find out to pop field at this point, which is at a distance r, so the delta phi m, we use delta because the potential is due to an elementary loop delta C. So this we write as I upon 4 pi delta omega, where delta omega is the solid angle subtended by delta C prime at the location field point. So this is the delta omega. We know the delta omega. So delta omega is equal to solid angle subtended by delta C prime at P. We write it as I upon 4 pi, this part we write delta S prime dot R by R cube. And as we did in the case of magnetic vector potential, we couple these two to introduce delta M. So this is delta M dot R upon 4 pi R cube. If we had delta M is the dipole moment which we introduced earlier, and we are considering an elementary loop so that we can assign a vector sense to it. If we have an extended source, then it can be broken up into elementary pieces, and the theory is applicable for each of the elementary pieces. And so for the circulation of the current is concerned, the current in all the intermediate branches it cancels out, only the peripheral current persists. So the when we sum the vector scalar potential due to individual elementary loops, then it adds up to the result of the entire extended loop. So let me calculate the B for this. Again delta, because it is applicable for an elementary loop. This is grad of delta phi m. So apart from this, this is minus mu 0 upon 4 pi, then gradient is operating on delta m dot r upon r cube. If we consider this origin to be lying with the center, then this is equivalent to minus mu 0 upon 4 pi delta m cross small r And we know from the theory of electrostatics that when the total charge is zero, the the dipole moment is independent of the field. However, here we have used the fact that we choose the origin of the coordinate system to lie at the center of the elementary loop. So this part has to be calculated. This part is minus mu 0 upon 4 pi. Then this part. One is the gradient of delta m dot r upon r cube plus delta m dot r times gradient of 1 by r cube. This part we know is 3r by r to the power 5, and for this part this part gradient of delta m dot r can be looked upon from the consideration of back curve rule that we have explained in the connection with magnetic electrostatic dipole. Here we shall calculate it in another way. We write this as, and for the alternative way you look at the calculation of field for electric dipole, and the part is delta mx times x delta my times y delta mz times z. This calculation, this way of calculating the thing does not require any remembering any vector identity of this. When this operates, only this term contributes this to a 0, and the result is I cap mx. Then this is 0, this is just a delta my, this is 0. Similarly, m vector. So this is delta m, this part is delta m. So we get the result this minus sign is taken into it, and here will be a minus sign which adjusts with it. So this is 3 . One could also calculate the field count taking this form. In that case, only change will be that r is replaced by r minus r prime. So it will be in terms of it will so the gradient of 1 by r is minus 3r by r cube is okay. For this part, it will be delta m dot r, capital R will be x minus x prime delta mx plus y minus y prime delta my plus z minus z prime delta mz. When it is being operated by delta, again it is m. In that case, that is, if we work with this notation, the result will be mu 0 upon 4 pi minus delta m by r cube plus 3 delta m dot r times r by r to the power 5. This is the, so we see that this expression for the field at the point at point P is exactly same as due to an electric dipole of moment delta n, which also stands in support of the fact that delta n indeed behaves as the dipole moment for a closed current loop. Thank you.